Hi everyone and welcome to my YouTube channel. In this video, we'll be discussing the IOQM 2023 paper, which is the Regional Math Olympiad in India. So far, for Regional Math Olympiads on this channel, we've uploaded the SMC 2023, which is the Regional Math Olympiad in UK. And in this video, we're going to just discuss the Indian Regional Math Olympiad. So, a little about the style of IOQM. The time allowed is 3 hours and we have 30 questions. As you can see, we have the first 10 questions are worth 2 marks each, the second 10, 3, and the last 10, 5 marks each. And the test is not a multiple choice exam, but all the answers are just 2-digit numbers. Okay, the other info here are just technical stuff. So I hope you guys excited. What are we waiting for? Let's get started. Alright, for the first question, we have n is positive integer between 1 and 1000, and they're defining mn to be the number of integers in this set. So as you can see, this is all of them are roots. So if you want to count the number of integers, that means we need to count the number of perfect squares among the numbers for n plus 1, for n plus 2 till for n plus 1000. And we're interested in maximizing the number of perfect squares and minimizing it, and then we just need to calculate the answer for a minus b. A rule of thumb here, as we said, the answers are 2-digit numbers, so that means they will always try to tell us something like that. So don't worry about it. For example, if they said find a minus b, then probably we're just going to find a and find b. It's not there is some kind of trick that you can just calculate a minus b, for example, without a and b. Anyway, let's think about it. How can we maximize or minimize the number of perfect squares among these 1000 consecutive numbers? If you think a little about it, then you will easily see that if you write the first few perfect squares, so 1, 4, 9, 16, 25, 36, 49, and so on, you will see that the first few are really close to each other. So here you can see that the perfect squares are very close. However, if you move on to big values, let's say 100 square, 101 square, you will see that now the distance is very large. So now they are not close anymore. So that simply means, with simple logic, if you want to maximize the number of perfect squares in an interval, like 1000 consecutive number, then probably we're going to pick very small. So probably n is 1. And if we want to minimize it, then we should go for n is 1000. And this is exactly what we'll be doing. So let's go ahead and calculate that. So for n equals 1, our set is simply 4n plus 1 we start with. So that means 5, 6, 7 till 1004. And now we need to count how many perfect squares do we have here. So the first perfect square clearly is 3 square, because it's 9 simply. And you can easily see that the last perfect square is going to be, you can try 30 square 30, it's going to be 900. So if you try 31, it will also be below that, but 32 will not work, so that means the last one is 31 square. So that means that simply a is the number of numbers in this list, which is 31 minus 3 plus 1, and that's equal to 29. Actually, if you think about this, then you might feel that this is wrong. And indeed you're true, because what if we, maybe like for n equals 2, we were able to get 32 square without losing 3 square. That means this is a better answer. We're gonna get 30 here. But if you like really just do this idea that we want to include this number, then that means you should have something like this. So you can just calculate n, and you will easily see that actually you will not just lose 3, but you will lose 4 even. So this is for sure a bad idea. So this is a bad idea, and hence indeed our work was correct. So n is 1 is the best one, and we got just a. Now let's go for b. We're gonna do the same thing, but the opposite. So for n equals 1000, first one for n plus 1 is just 4001, and we're gonna continue till 5001, and we're gonna do the same thing. What's the first perfect square that is greater than 4001? You can also do some approximation here. For example, you can try 60 square, it will work. Then 65, like 70 will not work, so you should try 65. 65 will not work actually, so 64 you will try it and it will work. So 64 is there, and the last one is actually just 70, because 70 square is just 4900. You can try 71, it will not work. Okay, so that means this is our list, and if we want to calculate the number of numbers here, then we do the same thing, 70 minus 64 plus 1, and that's just equal to 7. Again, the same discussion. What if for, maybe we pick this, and maybe we will be able to get rid of this without including a new number. But again, for the same reasoning, you can try that. You can try, 4n plus 1000 less than 70,000, and you will easily see that this n will include actually 63 square. So it's just the same thing, and indeed our answer is correct. And remember, the question asks us to find a minus b. That means it's just 29 minus 7, which is equal to 22. This is our final answer. Okay, so here our final answer was 22. We're done with question 1. Let's move on to question 2. Question 2, we're asked to find the number of elements in this set. By the way, don't be afraid of these mathematical notations. You can just read it a little by a little. So here we have a set. They're telling us a and b are natural numbers, clearly. A and b are between 2 and 23, no problem. And we have got this nice equation. The log base a for b plus 6 times the log base b for a is equal to 5. So we're probably going just to focus on that currently and see how exactly can we deal with something like that. So let's take this down here. So they told us that the log a b plus 6 log a b is equal to 5. How exactly can we deal with the log like this? As you can see, we have two different bases. Here we have log a, and here we've got log base b. Actually, there is like a very nice identity that maps all the logs to the natural log. I like this identity a lot because I can turn any log for any base into just the natural log. And this identity is the following. This thing is simply the log of b over the log of a. So you just take the log of this and you divide it over the log of the base, whereas of course this is the natural log, and we can do the same for the other one. Log of a over log of b. Guess what? What do we see? We notice that these two dudes here, if you they are just reciprocals. So if one of them is x, then the other is 1 over x. So we're just going to do that and find what is x. So let's set this guy here to be x, and that will mean x plus 6 over x is equal to 5, and this is a quadratic equation. Let's solve it. First of all, it's like this: x equal to 0 minus minus 2, 3. So that simply means that x1 is 2 and x2 is 3. So what does that mean? That simply means that the log a for b is just equal to 2 or 3, one of them. So that means that b is either a square or a cube, because the log of a square with base a is 2 and the other one is 3. Okay, so that means we just need to count how many pairs a square and how many pairs a cube that are in the range they gave us. Remember, the range they gave us is between 2 and 20, 23. So that means we just need to count how many perfect squares between 2 and 20, 23. And then do the same thing for the cube, but right now let's focus here. So how many numbers do we have, perfect squares, between 2 and 23? You can easily see that the first number here is 2 square, of course 4, 3 square, till the last number. You can also easily check that it's going to be actually, you can try 40, it's gonna be below that, but 50 is above that, so you just go for 45 and so on, and actually you will just see that it's 44. So 44 square is the last number, and hence the number of pairs here is equal to 43. Same thing we're gonna do exactly, but now a cube, 2 and 20, 23. Also the same thing, the first number is 2 cube, 3 cube and so on. You can see that 10 cube is less than, but you should not, you should go gradually here, because 12 cube is the last number actually, and the number of pairs is simply 11. So in total, the number of pairs in total is equal to 11 plus 43, and the answer is 54. Nice. So that means the answer here is just 54. Okay, next question 3. We are given two positive integers alpha and beta. We have this inequality, weird inequality, and we need to find the smallest possible value of beta. Alright. So we know that alpha over beta is between 16 over 37 and 7 over 16. And we're interested in beta. As you can see, here beta is in the denominator. So if you want, to find condition for beta, then we should put it in the numerator. And another thing, these numbers are less than, right now currently, they are less than 1. So a nice thing is gonna be flipping both of these. Of course, don't forget to flip the inequality as well. So now we've got 16 over 7 and 37 over 16. Now you can simply get the following: 16 over 7 alpha and 37 over 16 alpha. And actually, if you calculate these two numbers, 16 over 7 is just going to be 2.28. Of course, this is approximation, and this thing is gonna be 2.31 alpha. So if you just look at this now, of course, what we're gonna be doing is we're gonna try alpha equals 1, for example. If you try alpha equals 1, you will see that there is no number between 2.31 and 2.28. You can try alpha is 2 and see whether there is a number. You will see that there is no, and you will continue. In fact, just by looking at this, we can see, we can create an instant solution. If you choose alpha equals 10, notice it's going to be 20, 22.8, and here 23.1. So for sure, that means this is a solution. 23 works. But of course, in order to check the minimality for beta, you need to try the alpha, from 1 till 9, and check that actually none of them will work. Indeed, none of them will work, and this will be the answer. The minimal beta is 23. So the answer is 23. So the problem with these types of questions is that it's time consuming because of the number of cases and the calculations you need to do. Okay, right now let's do question 4. So we're gonna be doing it here. Question 4 is just, we have x and y, two positive integers, and we have this Diophantine equation, and we need to find the maximal possible value for x plus y. Remember, don't worry about that, just find x. Probably we're gonna find x and y. So if we just rearrange, we're gonna get this thing. Now, if you have some experience with divisibility, then you already can see that this thing has two factors, x minus 1 and this thing. So that means this thing is divisible by x minus 1. You can write something like this. If you think about it in mod x minus 1, if you take mod x minus 1, this thing, of course, it's 0, so x is going to 1 mod that. And this thing should be 0, but we already said that x is 1, so that means that x minus 1 must divide 2. Again, just like a simple mod argument, you should have some experience with mod. X minus 1 divides 2, this is very nice, that means that x minus 1 is equal, belong to either -2, -1, 1, or 2. It's a divisor of 2 after all, factor of 2. And of course, they told us that x is positive integer, so this is refused, this is refused. So that just leaves us with the option that x is equal to 2 and 3. So we should try both. So if you try 2, you will see that, right here, if x equals 2 to the 4 is 16, so 17 plus 23 is equal to y cubed, and you will see that actually there is this is just 40, so no solution here. But if you try x equals 3, then 3 to the 4 is 81, 81 plus 1 is 82, divided by 2, it's 41, 41 plus 23 is just 64, which is 4 cubed. Hence, in this case, y is equal to 4. So y is 4 and x is 3, that means x plus y is 7. Hence the answer is 7. Alright, very good. We're done with the first page. Okay, next. Question 5 is a geometry question. So let's draw it. Small diagram here. So first of all, we're going to start with a triangle ABC. Okay. Triangle A, B, C. We're going to put some midpoints, midpoint of AC. Midpoint of AC, it's what? E. And here is F. We draw the two medians. They intersect at G. Then we take the midpoint of this median and the other midpoint of that median here. This is G, the centroid, and Y is the midpoint of BE. This is Y, and this is Z. Okay, what's the question? The question is simple. They're telling us the area of triangle ABC is 480, and they're asking us to find the area of this triangle. Alright, so this is actually a very standard question, in which for sure we're going to be using the ratio between two areas. So if you're not familiar with this, you should keep it in mind. What's this theorem basically? if you have a triangle ABC and you have a point D here, then you should know that the area of ABD over the area of the whole triangle is just equal to BD over BC. So it's just this thing over this thing, and it really makes sense, because if you just drop the altitude, you can get an instant proof, because the altitude will cancel from both of the triangles since it's the same altitude. Okay, so this is very important. So probably we're gonna be using this more than once in order to, you know, go from this bad triangle into the good triangle, which is ABC. So first of all, before we do anything, we need to figure out the ratios. So usually, as you know, the median is really nice because G cuts it into 2 to 1. So this thing is 2 to 1 ratio. So like usually the best thing you can do here is, if you set this as 6, then you're gonna get that this thing is 3 Py, because Y is the midpoint, and this thing here GE is just 2, and that means this thing here is 1. Of course, these are just, you know, the ratios. They are not the real lengths. So that means GY represent 1/6 of the whole median. Same thing for, you know, the other GZ. Okay, now our game starts. We want to find the area of GYZ. So we want for sure to delete the bad points. What are the bad points? They are Y and Z. So first of all, let's delete point Z. So to delete point Z, you want to apply this theorem such that point Z is the point D here. So probably you're gonna do this. So now we can apply the exact theorem, and let's apply it immediately. GYZ is equal to, of course you can check that this thing is, as we said, 1, and the whole thing, this here, is 4. So that means it's 1 over 4. And now the area of GYC. Good, we deleted the point Z, as you can see. Let's continue. Now we're going to delete point Y. And exactly, we'll be doing the exact same thing, but now point Y is, you know, the point D, our original theorem. So now we're gonna have this first 1 over 4 times what? Again, this is, you know, 1, and this is 4. So still it's 1 over 4. But now, of course, the area of BGC. Okay, very nice. Now actually BGC, this is, you know, a well-known thing. If you have the centroid, then you should know that it divides the triangle into 3 equal areas. Like all of these are equal, you know, S, S, S. So that means this is just the third of the area of triangle ABC. So that means 1 over 4 times 1 over 4 times 1 over 3 times ABC. What was ABC? It was 480. Okay, so let's calculate that. 4 with 480, that is 120. 120 over 12 is just 10. So the answer is 10. Nice. Okay, next question. Let x be the set of all even positive integers n such that the measure of the angle of some regular polygon is n degrees. We need to find a number to count how many elements in x. Okay, this is a really standard question. You should just be able to know how to represent or how to find, if you have a regular n-gon, what is the angle of like what's the single angle of any one of them. Okay, this is really an easy thing. We can do it right here. So let's say we have n-gon, n regular gon. What is the sum of the angles? You know, this is a very well known thing. It's just n minus 2 times 180. So if you want to count to see just a single one, a single angle, you just need to define it divide it by n. This is because the total, so we divide it by n, we get, you know, since it's regular, each angle. So now what they're asking us is that this thing we want it to be an even integer. how many n's satisfy that they give us, you know, something like 2 times m. Well, if you just think about it, that means that if you divide this thing by 2, then it's gonna get an integer. So let's divide it by 2. If you divide this thing by 2, this thing, we want it to be an integer, so let's cancel the 2 with this thing, so it's gonna be 90. We want this to be an integer, so we want n to divide 90 times n minus 2. Here actually you can do 2 cases. If n is odd, you should know actually that n and n minus 2, they only can share 2 or 1 as their GCD. If n is odd, then for sure they don't share anything. So if n is odd, that means n divides 90. And remember, n is odd, so n can just take what is 90? 90 is 2 times 3 squared times 5. So you can just pick the any odd divisor. How many odd divisors do we have? 3 times 2. So here the number of divisors is just 3 times 2, that is 6. So 6 answers here. Here n is even. If n is even, then this thing will, you know, cancel a 2 and a 2, and we're gonna just have a remaining number here, that's n over 2. So n over 2 should be a divisor of 90. And again, this is just the same representation, but here of course we're allowed to pick anything. Like whatever you pick, n over 2 equals a divisor. N is gonna be 2 times something, so it's for sure gonna be even. So now you can count all of them. So that means 2 times 3 times 2, and that's equal to 12. So now the final answer should be, or the total, let's say, it's gonna be 6 plus 12, and that's 18. We're done. Actually, no, we're not done. Be careful. Here, the question is asking us to find, like we know that it's an n-gon, a regular n-gon. What does that mean? That means, think about it. If you have a regular n-gon, can you have a regular n-gon with when n is 1 or when n is 2? For sure no. So you need to actually cancel the n equals 1 and n equals 2 solutions, meaning that here when n is odd, we need to cancel the n equals 1 because we actually counted it here among the 6. Same thing here, we need to cancel n equals 2 because we also counted it here actually when this thing is equal to 1. So that means that we need to deduct actually 2 here and get 16. And now 16 is the final answer. So you really need to be careful in these types of questions, especially that this is, you know, a regional math Olympiad. You don't get partials. Either you get 0 or you get, you know, here 2 marks for each question. So like you need to be very careful and double check everything. Okay, next question 7. We've got a dice. It's unconventional. Let's see what are the conditions. We have 6 faces. Okay, they're marked from 1 to 6. 1 and 2 are opposite faces. Okay, they're telling us that each face is colored either red or yellow, so one of 2 colors, but the opposite faces are always the same color. So for example, 1 and 2 are opposite, so that means they have the same color, red red or yellow yellow. 2 dice are the same if one can be rotated to get the other. So you can, you know, catch the dice and play with it. You can rotate it. If you rotate it, it's gonna be all the same. And of course the question is, you just need to count how many different or distinct dice you can design. Okay, you need to have a drawing for this. Let's simply draw a dice. Okay, something like this. Let's say that 1 is here and 2 is here. Of course, we're just playing we can rotate. So we can assume 1 is here and 2 is there. Furthermore, you can actually rotate around this axis. You know, this axis, you can do that. So you can actually assume furthermore that this is 3. And if you do that, now you'll just have a single shape. So now actually you should not worry about the rotating anymore, because now you cannot rotate anymore after all of these assumptions. So once you put the 1 below, the 2 is instantly above, and then you will rotate it until you make a 3 on the right. Now actually you will see that 4 and 5 and 6 are just going to be one of them here, one of them here, one of them there. So that simply means that 4 has 3 places, then 5 has 2 places, then 6 has 1. But then we need to color them. So for each opposite faces we have two possibilities. So 2 times 2 times 2, that means this is, you know, times 2 to the 3. So basically it's the answer is 6 times 8, this is 48. Alright, so the answer is 48. Where was it? Okay, done. Next, we've got a tiny question. We've got some tiles, one of them is 2 times 2, and we also have 7 dominoes that are 2 times 1. We need to tile a rectangle of like 2 times 7, 2 times 7, and of course no overlapping is allowed. Okay, so that let's first of all draw that rectangle. One, 2, 3, 4, 5, 6. Okay, now if you think about it, let's just say what do we have? We have tiles. We have this tile, and we have 7 tiles of this shape. So here we just have 1, here we have 7. Okay. So now we need to tile that. So as you can see, if we use one of them, one of these, then it's just gonna be something like this or this. But if you use this, then we either going to do something like that, or actually you can do it like this. You can put it, rotate it and put it in this shape. But if you put it like this, then you should also put another one below it. So now you're going to have also a 2 times 2. But this 2 times 2 is not this version, but it consists of 2 of these. So how are we going to count? We're gonna simply do cases. So we're going to count how many of the 2 times 2 do we have. And when I say 2 times 2, I don't just mean this, but I mean these if we combine 2 as well. So let's say first of all we don't have any. So if it's 0, then that means you have 7, and that means you only going to put the 7. So it's just 1. So here we just have a single 1. The other case, if we have the number is 1, then here that means you're going to have something like this, and the others are just like that. So you're gonna have 4 of these, and sorry, not 4, 5 of them, and a single one of this. So as you can see, just first of all to fix the shape, how many locations you can do. Either you're going to put the leftmost, or here, or here, or here. So you can, like, in total you're going to have 6 of them. So you're gonna say 6 times something, 6 times. But then remember that this thing here, you're either going to pick it the special tile 2 times 2, or you're going to create it like this. So it's times 2. So that means in this case it's 6 times 2. Let me move this a little here. So 6 times 2, that is 12. Let's move on. What if we have 2? So now if we have 2, then we're going to have something like this. And how many of them? Now we have 2 of this, so it's 4, and we're just going to need 3 of these. Okay, again, how many ways to permutate these? You know, it's 5 factorial over 2 factorial times 3 factorial, because these are the same. This is, you know, just to know the shape. So that means it's 5 times 4 over 2, so it's 10 times something, y times something, because as we said, we need to see whether we're going to use the special tile or not. So either we're going to use the special tile or not. If we don't use it, then, you know, it's just one way, so you can think about it as 1. Or if we use it, then either it's going to be the left one or the right one. So that means you can have 2 here. So we simply multiply this by 3 and get 30. Okay. Next case. 3. By the way, there's an important thing here. That is that when we're doing this, you should make sure that you don't run out of these. So now actually if you count them, we have here 2, 2, and here 3. So 3 plus 2 plus 2 is 7. So yes, we're safe. But this is something you should be careful, because imagine that, for example, we got that we need 8. So we're going to refuse this case. Anyway, now it works, so no problem. Now if we have 3 of them, so that means we're going to have this, 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 and now we have a single one of them. A single one of these. Of course, now how many ways? You can just look at this, either the rightmost or here or here or here. So it's gonna be 4 times, and now to create, you know, these, how many ways you can create it. Again, either we're not gonna use it, so it's 1, or if you use the 2 times 2, then it's gonna have 3 locations, so it's gonna be 4. So 4 times 4, that is 16. So in total, it's 1 plus 12 plus 30 plus 16, and that is 59. So the answer is 59. Where is it? Okay, let's go ahead. Okay, number theory question 9. Find the number of triples ABC, positive integers. AB is prime, BC is 2 primes, ABC is not divisible by square of any prime, ABC is less than 30. Okay, less than or equal to 30, of course. Let's start with AB is prime. So if AB is prime, that means product of numbers is prime. This is impossible unless one of them is 1 and the other is prime itself. You know, we usually represent primes with P, Q, and R. So I'm just going to be doing that. So here we have 2 cases. Either A is a prime or B is a prime. So let's, you know, do the cases here. So case 1, A is a prime and B is 1. Remember what they told us? They told us BC is 2 primes, but BC is already like just C. So that means C itself is 2 primes. So C is just equal to Q times R. Okay, very good. Next, they told us that ABC is not divisible by a square of any prime. What is ABC? It's PQR. So PQR is not divisible by the square of any prime. What does that mean? That simply means that, you know, we cannot have P equals Q, because if P equals Q, then we can have P square. So it's divisible by a square of prime. So that just means that P, Q, and R are distinct. Okay, nice. So P, Q, and R are distinct. This is, you know, the condition. And now they told us ABC is less than 30. So that just means that PQR is less than 30. Okay, can you get 3 primes that are distinct and less than 30? They must, you know, their product is less than 30. Well, you can try the minimal 2, 3, 5, and you're gonna see that in fact they multiply to 30. So that means this is the only option. But now you need just to because P can take any of these values. So P can take either 2 or 3 or 5. Then Q and R are going, to take the other values, but it doesn't matter because Q and R, their product is C, and we just care about, A, B, and C. So that means here the answer is just 3. So the number of A, B, C is 3. This is very important. Do not count the number of P, Q, R. We are interested in counting the number of A, B, C, because if you choose Q and R to be, 2, 3 or 3, 2, it will not matter for A, B, C. Okay, so now we got this for the first case. Second case, A is 1, B is a prime. So now BC is P times some C, so C itself is a prime. So now we have this, and of course again ABC is just PQ, and we know that PQ is not divisible by square of a prime. That means P and Q are distinct, and we know the main condition, PQ is less than 30. So we need to count how many primes that their product is less than 30, and you can easily do that by let's write the first primes, so make it easier for us. 7, 11, 30, yeah, that's enough. So now, for example, you can pick P is 2. How many do we have? Q should be less than 15, and you should not choose 2, so you've got 5 here. P is 3, then it's less than 10, and you can just pick 3 here. If P is 5, then it should be less than 6, and you can just pick 2 of them, 2 and 3. If P is 7, then you can just pick 2 again. But if P is 11, then you can just pick 2, so it's 1. You cannot pick 3. So if P also is 13, then you can just pick 1. So in total, A, B, C. Of course here P and Q, like you can just count the number of P and Q. It will work. So let's just add that. 1 plus 1, 2, 2, 2. So here 6, 9, 14. And don't forget to add them. So 3 plus 14, that's 17. So the final answer is just 17. Okay. Next, we've got a sequence question. So we're given that A0 is 1, A1 is -4, and we've got a recursion. And find the number of positive integer divisors of this number, A50 square minus A49 times A51. Okay, usually the first thing you should try in these types of questions is to evaluate the first few terms in order to explore the sequence. Maybe you get something nice about it. So this is exactly what we'll be doing. So first of all 1, then -4. Then let's calculate. Of course, we should keep an indicator here, an index. A1, A2. So to find A2, we're going to take -4 times -4, it's 16, minus 7, that is 16 minus 7 is simply 9. Next, let's calculate A3. Okay, again, -4 times this, 36, minus 7 times this, so it's plus 7 times 4, 28, so it's going to be negative, and it's going to be -8. Okay, so you see that there is nothing that much special here. So what exactly can we do? How exactly can we calculate this thing? For sure we're not going to continue till we get A50, because this will consume the whole time for the exam. Okay, so basically if you look at this thing, we should have a look at it. This thing is it random? It doesn't seem that random. Look here, 50, 49, 51. So that means that we should just consider something like this. Let's define f of n to be an square minus an minus 1 times an plus 1. Our question is find f of 50. So maybe you should, this thing itself is nice. Let's try to calculate this thing. So what is f of 1? F of 1 is just a1 square, that's 16, minus 1 times 9, so this is equal to 7. So f of 1 is 7. What about f of 2? F of 2 is a2 square, so 81, minus negative 4 times negative 8, so 4 times 8, that's 32, that's 49. Okay, I think you see something nice. 7, 49, 49 is 7 squared. In fact, if you calculate also f of 3, you will get that it's just 343, that's 7 cubed. Can just find a4 and calculate that to double check. And of course, because this is not a proof, they're not asking us about the proof. And for sure, this thing it's not a coincidence. That you got 7 squared, 7 cubed, and then suddenly it will break. No, that means this thing, like f of n simply is 7 to the n, so this is just 7 to the 50, and they asked us to count how many divisors do we have here, so the answer is 51. So the answer here is just 51. Okay, next they are telling us positive integer m is expressible like m square is equal to this thing, and we need to find the maximum value for m minus n. Okay, m square is this, so let's work with that. Is equal to 4n square minus 5n plus 16. As you can see, this is a quadratic equation in terms of n, so it just makes sense to make it a quadratic equation for sure. Okay, now actually here is a very nice thing that you should keep in mind. Whenever you have a quadratic equation and you know that you have an integer root, what does that mean? That means that your delta should be a perfect square. It's a very standard idea. You can just calculate the delta, and it must be a perfect square. Otherwise, how are you going to get like an integer root? That positive, negative root, delta. So this thing must be a perfect square. So what is the delta? Delta here is 25 minus 4 times 4, 16, times 16 minus m square. So this thing should be, something, let's call it a square. So what does that mean? That means that 16 m square minus a square, just expand it and move a square here. This thing is just gonna be 16 square minus 25, which is simply 231. And this thing, you can factorize it. Now actually we're kind of done, because this thing is a difference between two squares, so you can just simply do this. This thing is what? 3 times 7 times 11. And now you have some possibilities to discuss. Luckily, you don't need to count all the divisors, all the possibilities, the 2 times 2 times 2, which is 8. No, you don't have 8 cases, because you know that this thing is greater, so that only leave you with half of them, so you just have 4 cases. So 4m plus a, 4m plus a is one of these cases. 11 times 7 times 3, and 7 times 11, and 11 times 3, and 3 times 7, and for m minus a is just the complementary, so 1, 3, 7, and 11, and you will just get that 8m. If you add them, you can get the value of 8m, and you'll see actually that m itself is one of these values: 29, 10, 5, 4. So now for each one of these, you're gonna plug it here, you're gonna find n, and it's really easy because you can just factorize it, since the roots are integers, so you can factorize each one of them. For each one of them, you're gonna get a solution, but remember, we need to maximize m minus n, so we need to have m and n from each other. So you will see that if you pick m equals 29, and m equals 10, you're gonna get here n is equal to 15, and here negative 4. So that means m minus n is just 14, which is our answer. So here the answer is 14. Next question, we've got a polynomial, a cubic polynomial. A, B, C are integers, C is odd, and Pi is just, P of I. They're giving us this nice identity. Sum of 3 cubes is 3, P1, P2, P3, and we need to find this thing. Okay, this seems very nice. You should know some factorization. You easily know that this can be factorized. So let's just do that. So let me remind you of the factorization of this. P1, P2, P3. This is equal to half times the sum times P1 minus P2 square plus P2 minus P3 square plus P3 minus P1 square. This is very important and common identity that you should need to keep in mind. This thing is 0, they told us, so that means either this thing is 0 or this thing is 0. Of course, if this thing is 0, that means all of them are zeros. This, and this, because they're all non-negative. So that means all of them are equal, actually. Okay, so that leaves us with two cases. So case 1, the sum is 0. Let's have a look here. You can calculate, P1 and P2 and P3. For example, P1 here is just 1 plus A plus B plus C. And you can do the same for the others. But remember, here they told us something which is C is odd. So perhaps you should think about the parity. If you do actually think about the parity, you will see that if you add P1 to P2 to P3, you're going to get here, 1 for the 1 and 3 and 2, you're going to get an even thing. You can do the same thing here. You're going to get also an even number. Here, even number. But here you're going to get 3C. C is odd. 3 times C is odd, so that means the sum of the 3 P1 plus P2 plus P3 is odd. So it can never be 0, so this case is refused. So that only leaves us with case 2. And case 2 simply tells you that P1 equals P2 equals P3. Now how can we continue from here? Well, you've got two ways here. Either you can do the standard way, which is, P1 equals P2 equals P3. So you can calculate P1, P2, and P3 and maybe evaluate A and B using C. Because you just have two equations, 3 variables. You cannot find A, B, and C. You can just find A and B using C. And then remember that here P1 equals P2. So these are the same. So it's actually, this thing is just 3 times P1 minus P0. So in fact, you just need to find like P1 minus P0. You can easily see that it's just 1 plus A plus B, and you will get actually an answer here. The other way you can do is really a smart way. I'm going to tell you the trick here that we can do. So let's discuss a little about polynomials. Remember, if you know that P of alpha is 0, then that means P of x, you can factorize x minus alpha. So you can write it as x minus alpha times something, because now if you plug alpha, it's going to be 0. But what if I told you P of alpha equals beta? Is it useless? Not really. Now what you can do is simple. This thing minus beta. Now alpha is a root for this because it makes it 0. So that means this thing is x minus alpha times qx. So now we can move it here. So that means P of x is equal to x minus alpha qx plus beta. Very nice. Why exactly do we care about that? Well, remember, we know that P of 1 and P of 2 and P of 3. Let's say this is whatever, like let's call it alpha maybe. Then P of x minus this alpha, this thing accepts 1 as a root, 2 as a root, 3 as a root. So that means actually that this thing is just equal to x minus 1, x minus 2, x minus 3, and times some stuff, qx. But guess what? This thing is cubic. This already is cubic. So this thing, is just a constant number. And also, the coefficient of x cube is 1. So here the coefficient of x cube is 1. So we don't have anything. So actually this is correct. This is, the identity. So of course we can move it there. And this is our polynomial. Very nice. Remember, they asked us to find p1 minus like 3 times this. So let's simply do that. Of course, p1 itself is alpha. You can plug here 1. Or remember that we just said that these guys are alpha. So this is 3 and alpha minus p0. What is p0? Plug it here. So negative 1, negative 2, negative 3. That is negative 6. So negative 6 plus alpha. And this is just equal to 6. So 3 times 6 is just equal to 18. And this is our answer. So here, our answer is just 18. Okay, we're done with that page. Let's move on. Okay, question 3, geometry question. The x-radii of triangle 10.5 and 12 and 14. And they gave us that the sides of the triangle A, B, and C are the roots of this cubic equation. P, Q, and R are integers. Find the integer nearest to root P plus Q plus R. Okay, so this question is about the x-radii. First of all, let's discuss what exactly are the x-radii. So, if you're familiar with this, the x-radius, okay, I'm gonna do it here. What is an x-radius? So if you know, we have a triangle ABC, and we have a circle that's tangent to the 3 sides internally. This thing we call it the in circle. So this is the in circle because it's inside the circle, in circle. And what do we call its radius? Small r. We call it the in radius. But guess what? Here they're telling us the x radius, so it makes sense that we can have it outside. So actually we can draw some circle like that, and this circle is called, because if we have A, B, and C, then this circle is called the AX circle, because there's not just one of them. You can just do the same here and draw another circle here. So you have 3 of them. Each one of them is gonna have a radius, and what do we call its radius? If the in circle has in radius, then this one should have basically x radius. So we call it the x radius, and this is exactly what's in question, x radii, because we have 3 of them. So each one of them, they gave us the length of it. So now we know what is RA and RB and RC. Very good. The nice thing about it is that we can actually create an identity here, or a relation between RA and the sides of the triangle. What is it exactly? Well, it turns out that, as you know, the centers of these this one is I, the in center, and this one is IA. Of course, if you come here and drop from the tangent, for sure you're gonna get a 90 and a 90. Furthermore, this is just RA, the x radius, and this one is small r, the in radius. And if you know some geometry here, then you should know that this thing, it's well known, it's S minus A, and this thing is S. What is S? S is the semi-parameter, so it's A plus B plus C over 2. Okay, so if we know that, how can we find a relation for RA? Well, look at the similarity. We have a clear similarity here. We can simply write RA over R is equal to S over S minus A. Hence, RA is just RS over S minus A. And if you're familiar with this, RS is actually the area of the triangle. So let's call it something like maybe delta over S minus A. So if we call that, now we know RA, RB, and RC. So that means we know delta over S minus A, and delta over S minus B, and delta over S minus C. Because we have delta everywhere, so you can actually here do a ratio thing to get rid of the delta, so you'll have just s minus a over s minus b over s minus c. So if you just think about it in this way, this thing is just equal to, of course you need to flip them, so like this, and I think it was 12 and 14. Now we can, you know, play with this a little, multiply everything, divide everything by 2, so it's like this, and now you can see these share 3 and these share 7, these share 7. So if you multiply by 21, this is 1, 21 over 24 is 7 over 8, and this one is 21 over 28 is 3 over 4. Okay, it makes sense to multiply by 8. And guess what? We get this nice thing, 8, 7, 6. So that simply means that s minus a is equal to 8t, s minus b is equal to 7t, and s minus c is equal to 6t. So that means that if you add all of them, you're going to get 3s minus a plus b plus c, which is 2s. So s itself is just equal to 21t. Nice. So now we found s and s minus a, s minus b, and s minus c. Now our goal is to find t. How do we find t? Remember, here we know Ra, and now we were able to find s minus a using t. So can we find delta using t? If we can, then we can find t for sure. Okay, remember, delta is just the area. How can we find the area using t? Remember, we've got many formulae for the area. One of them is Heron. Heron is very nice because it tells us this using s minus a, s minus b, and s minus c, and we know all of these guys in terms of t. So we can plug all of these, and we're gonna get t to the 4. So this thing is t squared. Now think about it. We're gonna have here the root of 21 times 8 times 7 times 6. So this thing is t squared. Let's think about it. 6 here. Here we get a 2, so it's 4. Here we get 3, so it's 7. So 6. Okay, now it's 7 with 7, they cancel, and 4 itself gives us 2. So 7 times 2. Okay, so this is basically 14 times 6t squared. Nice. So this is delta. Okay, now we can use any one of them. So let's say Ra, it was 10.5, is equal to 14 times 6t squared over, what was this minus a? 8t. Of course, this is equal to what? T cancel with t. T squared with t, this gives us t. And 8 is just gonna be 2 here. And 7 times 3, 21. And guess what? This is just 21 over 2. So that means that t is 1. Nice. So t is 1. That means we found everything. That means s minus a, s minus b, s minus c. This is 8. This is 7. This is 6. And s itself is equal to 21. So we can find a, b, and c. You can easily see that a, b, and c. A is just going to be equal to 13, 14, and 15. Okay, very good. We got the sides of the triangle 13, 14, 15. Are we done? Not yet, because they're trying to do some tricks here. The sides of the triangle that are 13, 14, 15, they are the roots of this. And they want us to find p plus q plus r, the root of this. Remember, p, how do we find p, q, and r given the roots? How can you find the coefficients if you have the roots? Of course, you can use Viet relations. But here actually even something easier. Instead of finding p and q and r, here they're asking us to find p plus q plus r. So can't we use the idea that this thing here is just x minus 13 times x minus 14 times x minus 15, because we've got, the 3 roots. Can't we use it by plugging a suitable value for x? For example, if you plug 1, x equals 1, you're going to get something like this. We don't want that. We want all of them to be the same sign. So what should you plug? Well, easily, if you plug just -1, it's gonna do the job. So -1, you're gonna get -1 minus b minus q minus r. This is exactly what you want. So that means, let's return here. That means that -1 minus, let's call it, s, p plus q plus r. This thing is gonna be equal to, remember, we already have x minus 13, x minus 14, x minus 15. So if we plug -1, that's gonna be negative, 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 so negative here. In fact, you're just gonna have, s plus 1 is equal to, and what was it? -1, -13, so it's 14. 14 times 15 times 16. Okay, very good. You can easily now find s. So what is 14 times 15 times 16? You can easily calculate it. It's gonna be 3,360. So this thing -1 is equal to this thing. Remember, our goal is to find root s. So this is equal to root 3359, and we need to find the nearest integer to this. So you can check that this thing is actually between 57 square and 58 square. It's closer to 58 square. So this thing actually approximate as 58, and this is the answer. Again, some not nice calculations. Okay, we're done with that. Now we've got a coordinates question. Okay, let's draw it right away. They're giving us B is the origin of ABC. Okay, I'm gonna draw it here. So they're telling us that we have a triangle B, A, and C. We can extend this to a point D such that they have the same, lengths. We can extend this so that this length is, double of it to point E. This is 2 to 1, and we can extend this to get 3 to 1. And they're giving us that B is the origin, 0, 0. They're giving us the centroid of the triangle ABC. They're saying that the centroid G, they're saying that G is 32 and 24. And they're saying that the centroid for the big triangle, this one, the big triangle, this one is K, and they want us to find the length KG. Okay, let's first of all, since we know we have some coordinates, let's just calculate the coordinates of the other point. So let's call this XCYC, and let's call this XAYA, and for sure we can find everything in terms of that. So easily, because B is the origin, we can know that this is 2XC 2YC, and easily this is a -3XA -3YA, and now E is a little naughty, but you can easily do a vector EA is just 2 times AC, and you can easily see that actually E is just gonna be 3XA minus 2XC and 3Y minus YC. Very nice. In fact, you can use complex numbers here, but if you're not familiar with complex numbers, then no problem. You can also use just like Cartesian coordinates as well. So let's do it with Cartesian coordinates. Right now, let's find the coordinates of the centroid, because they want us to find, the centroid of the big triangle. So we need to add them and divide them by 3. 2XC minus 3XA plus this plus 3XA minus 2XC. Wait a minute, they cancel. Very nice. So they cancel, they give us 0, and the other one is gonna give us 0. 0 over 3 is 0. So that means a surprise. B is K itself. B is the centroid. Nice. So that means the question is asking us to find BG. Okay, nice. This is easy. This is just roots of this thing square plus the other one square. So the answer is just BG is equal to root 32 square plus 24 square Okay, you can take 8 squared as a common factor, so 8 times root, and what's gonna remain here? 4 squared plus 3 squared. Okay, this is 8 times 5, that's 40. So the answer is 40. Nice. Next, also a geometry question. We have a unit square, ABC, ABCD. Okay, let me also draw shape here for you. Okay, so we have a square. Let me do it here. A, B, C, D. We're gonna pick 2 points, 2 random points, M, N, such that the perimeter of this triangle, MCN, is 2. So they're giving us the perimeter of it, it's 2, and don't forget that this is a unit square. Next, we need to draw this triangle. We need to take the circumcenter of it, let's say O, and we need now to draw MON, and we need to take the circumcenter of that triangle, MON. So let's say some point P. Next, we need to connect OP and connect OA. And they're telling us to find, or they're actually telling us OP over OA is something, M over N squared and whatever, find M plus N. So that means we just, need to find OP over OA. Very nice. Of course, right now we know that this is equal to this, equal to this. So we can replace OA with, ON or whatever we want. And don't forget that P is the circumcenter of the triangle MON. Okay, how can we proceed with this question? Okay. So here, of course, you can either go for a synthetic solution or you can go for a coordinate solution. The main reason is that you have a unit square. So it's really nice to use coordinates here. So let's go with coordinates. So I'm going to say that A 0, 0, B is 1, 0, D is 0, 1, C is 1, 1, M is going to be alpha, 1 alpha, and N is beta 1. Okay, nice. Now, of course, what we can do is we can brute force, the perimeter idea. The perimeter is 2, so we can find a relation. We can find alpha in terms of beta. And then, of course, we need to find the circumcenter O, and then the circumcenter P. This thing is a little, not that ugly, but it is actually kind of ugly, because finding the circumcenter is not an easy task. So can we do some tricks here? Well, actually, again, this is not, a proof written contest. It's just a regional math Olympiad. So we can actually play on the questions when they give us some free stuff. For example, here, did they put any condition on M and N? Yes, only one condition, that the perimeter is 2. So that means actually we can play with M and N. We can play with one of them, and the other one is going to be determined. So what we can easily do is we can, for example, make this triangle isosceles. So maybe, this is going to give us some nice results. What does that mean? That means that simply alpha is equal to beta. If we choose alpha is equal to beta, and then try to find, what's the condition, that the perimeter, what's the exact number of alpha, that's gonna make our life much easier. So let's just do that. Let's assume, that this thing is isosceles triangle. This is equal to this. That means that alpha is equal to beta. So this is 1 alpha and this is alpha 1. And let's just find what's alpha. So this is, 1 minus alpha, this is 1 minus alpha, and because this is now isosceles, this is root 2 times 1 minus alpha. So that means we have 2 plus root 2 times 1 minus alpha is equal to 2, which means 1 minus alpha is just equal to, okay, you can cancel that, root 2 over root 2 plus 1, you can multiply by the conjugate here and here, so it's 1, so it's actually 1 minus alpha is just equal to 2 minus root 2. So that means that alpha itself is just gonna be equal to root 2 minus 1. Very nice. So that means this thing is just root 2 minus 1. Same thing for this, root 2 minus 1. Of course, root 2 minus 1 is between 0 and 1, so it works. Okay, you see, so we just played with the idea that they did not really fix m or n. They, gave us one of them is random. Okay, so now we found m and n. Now how can we find o? Well, remember, what we know is that o is the circumcenter of this triangle. So if we take the midpoints of this, let's call it t, the midpoint, we know that ot is perpendicular over mn. In fact, what is the coordinates of t? The coordinates of t, because it's the midpoint, it's 1 over root 2 and 1 over root 2. Yeah, let me check, just did not make any mistake. Root 2 minus, okay, root 2 minus 1, so 2 minus root 2. Yeah, no problem, that's it. Okay, so this is t. So t was 1 over root 2 and 1 over root 2. Very nice. So now, what you can notice is that t lies on the line x equals y, right? This is, an observation. T lies on the line y equals x because, the x is the same as 1. So that means if we draw the diagonal AC, the diagonal AC is gonna pass through point T. It is going to pass through T. But is it perpendicular over T? So if it was, then that means that all of these guys are going to be collinear, which is super nice. Is it? How do we check? We simply check that, y equals x, is it perpendicular over the line mn? Just find the slope of mn. The slope of mn clearly is just -1. So yes, they are actually. They multiply to -1, so that works. So that means that indeed they are collinear. Furthermore, now we need to, of course, our goal is to find O. But if you have a look right now, like at point O, that means that point O right now lies on the y equals x. So, you can just say xx. So basically, we want to find the coordinates of O. So we know O is xx. So that actually gives, the fact that this is equal to this. Now we should just check the other condition, that these two guys are equal. And this should give us, the coordinates of x, or what is the exact value of x. So this distance is, of course, x squared plus x squared, the square of it. It's so we have simply 2x squared is equal to this distance. Is just you apply the distance formula and you get x minus 1 squared plus x minus root 2 minus 1 squared. So the 2x squared will kind of cancel here. We can take 2x and 2x something here. So 2x, and here we're going to have 1 plus root 2 plus 1 minus 1. So this is actually just 2 root 2x, and here we're going to have 1 plus root 2 minus 1 squared, and this is actually, this thing squared is just 3 minus 2 root 2, so it's 4 minus 2 root 2. So x is just, can divide by 2 and divide also by root 2, so root 2 minus 1. Nice. So x is root 2 minus 1. So that gives us the coordinates. Oh, actually, now if you look at it, we have a nice thing. Root 2 minus 1, this is root 2 minus 1. So that means this is actually parallel to the y-axis, and this is parallel to the x-axis. Oh, this is very nice. If this is parallel and this is parallel, and that means that this is actually a right triangle. Oh, this is very amazing actually, because what's the if you have like a right triangle, then what's the circumcenter of it? It's T. So I guess what? P is T. So that means this point is P, and that means that this is P. So we now know all the coordinates. But guess what? Actually, like in fact, that just means that this is 45 degree, because it's isosceles triangle. This is 45 and this is 90. And they asked us to find OP over this. OA, basically it's this also. So that means this is just the sine of 45. What is the sine of 45? It's just equal to 1 over root 2. So now we can return to the question. And they told us that this thing, which is 1 over root 2, if you square it, it's 1 over 2. So m over n is 1 over 2. They want us to find m plus n. So of course they are like relatively prime, so that means m is 1 and n is 2, and thus m plus n is just 3, and we should be done. Alright, now for question 16. The 6 sides of a convex hexagon. So we have a convex hexagon, and we know that all the sides are red. Each of the diagonals we're going to color with either red or blue, but of course the sides are red. If n is the number of colorings such that we have this condition that all the triangles in this hexagon, each triangle has at least one red side, we need to find the sum of the square of the digits of n. Okay, so basically we need to find n, and then of course just add the squares of the digits. Okay, so let's try to draw that and visualize everything they told us. So let's draw a hexagon. And all the sides are red, we know that. So now if we think about the diagonals such that each triangle has a red side, for example, any triangle that's going to have the sides is safe, because these guys are already red. So that means if we take this diagonal, then this triangle is safe because it has two actually, not just one. So for example, if we have this side and we pick any triangle like this, it's going to be safe. So you can think about it, and you will see that the only thing we should be careful about is this triangle. This triangle, if we color, for example, blue, 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 these three diagonals, we're going to be in trouble. The same thing exactly, we can look at the other triangle, which is this one. We also need to be careful with this triangle as well. However, if you look at any other triangle, for example, if we draw this diagonal, then you can see easily that any triangle that's going to have this diagonal is going to be safe, because it's going to contain a side which is already red. So that means we should just worry about these two triangles, this one and this one. So now it's very easy for us to count how many good configurations do we have, because now each of these long diagonals have two possibilities. They can be whatever they want. So that means 2 to the 3 times, and now how many good triangles here? Of course the total is 8. 2 times 2 times 2. However, we need to rule out the bad triangle, which is blue, blue, blue. So it's actually 7, and the other one 7 as well. So simply this is 8 times 7 times 7, which is 392. And remember, the question asked us to find the sum of the squares of the digits. So basically the answer is 3 square plus 2 square plus 9 square, and this is just 94, which is the answer. So let's go write that. So 94. Okay, that was an easy combo question. Let's move on. We're done with this page. Okay, question 17. Question 17, we're given a set A, B, C, D, E, such that they are ordered, they are distinct. A is greater than 0, so it's at least 1, and E is less than 100, so it's at most 99. And we know, of course, they are integers. They're telling us D is the average value of the fourth element. So if we consider all these tuples in set S that satisfy this, then D is the average of like capital D is the average of small d, of course taken over all elements of S. Find the largest integer less than or equal to D. So basically we need to find D, and then going just to find that. So of course, what's the average? The average, that means we're going to write all these possible sets, and we're going to take in all of them the D's, we're going to add them up and divide them by the total number. Okay, so let's think about it. What's the total number? How many total, like what's the cardinality of S? It's very simple actually. You're just going to have, numbers from 1 to 99. If you just choose how many we have, 5 numbers, that's going to be enough. So it's actually just the total is 99 chooses 5. Basically this is the total, so we're going to divide by that. Now we just need to figure out what's the sum sigma d. So let's go and find that. Okay, let's do it here. So right now the cardinality of S, as we said, is 99 chooses 5. Now let's figure out how we're going to add all the values for D. Okay, so now if you think about it, if D is some number, let's call it K, then remember we know A is less than B less than C less than K. So how many ways we can choose A, B, C? This is actually simple, because the number of A, B, C, you just need to choose numbers from 1 till K minus 1. 3, you need to choose just three numbers, which is simply can be done by K minus 1 chooses 3. And of course, how many E's now? Remember, E is just between K, it's basically between K plus 1 and 99. How many numbers do we have here? It's simply 99 minus K. So that means in our sum, the sigma of possible D's, where D is in S, is simply just equal to the sum K, because we're adding, remember, D for each value for it, times 99 minus K, which is the number of E's, times K minus 1 chooses 3. Of course, you can see that the first value for K, oh actually, yeah, the first value is going just to be 4. Yeah, because D cannot be 3. So it's going to start from 4, and we're going to end with 98. So we just need to find the sum and then divide it by the cardinality of S. So how are we exactly going to find that? As you can see, this is a combination sum, so we're going to use some tricks here for the combinations. So you really should have some knowledge and experience with combinations. This is highly recommended to solve these types of questions. So for example, here we have K minus 1 over 3 chooses 3. So if you look at this K, you can easily put it inside by doing this trick. You just divide and multiply by 4, And we know that if we have k over 4 and this thing, then we can just include it inside. So let me just write here, okay, 4 outside. Now we have the 90 minus k, and now this trick, you know, this is very important. Just to remind you, I just use here a chooses b is equal to a over b times a minus 1 chooses b minus 1. This one is a very important formula you should keep in mind. Let me drag it and put it here. Okay, so now of course still k is from 4 to 98. Okay, now this is much simpler. Now how are we going to deal with this? We still have a k, it's a problem. So we're going to use the exact same trick. If we want, you know, to do this again, then we're just going to need to have k plus 1. So here we're going to make k plus 1 by simply doing this for sigma, or actually now I'll just do it, you know, 100 minus k plus 1, and I'm going to expand it here and here. So that means here I have 100 and sigma k chooses 4 minus here now it's k plus 1 times this, so I'm going to make it like the same trick. Now it's k plus 1 chooses 5, and you know the same k is from 4 98 and here 4 98. Okay, now this is easy, we can calculate this one easily. How do we calculate these? Of course we're going to use the so-called hockey stick identity. This is very important to keep in mind. It's always going to help you evaluate sums of combinations like that, when the base below is fixed and the number is just, you know, moving consecutive. So if we just use the hockey stick identity, then we have here actually it's, you know, take the 5 outside, so this is going to be 20, and now this is going to be 20 as well. This thing, if you apply the hockey stick identity, it's going to be 99 chooses 5 minus, okay, now we don't have a 5 here. This is of course from 5 chooses 5 till 99, so it's actually 100 chooses 6. Okay, very good. So this is just the numerator, and now we need to divide it by that. So you will see that this will, you know, cancel. So basically the answer is going to be 20 minus 100 chooses 6 divided by 99 chooses 5. What's that? Okay, if you just, you know, put the combinations for that, then everything will cancel. This thing actually is just going to have the 6 here, the 100 is going to be here. Yeah, everything else will cancel. 100 exactly, so it's just, you know, 100 over 6, which is 350. So this is just 20 minus 50 over 3. We can take the 10 outside, so this is 200 times 2 minus 5 over 3, which is just equal to 200 over 6. Oh, sorry, over 3. Over 3. Okay, so simply we cannot, of course, simplify this anymore. So now what's the answer for that? Remember, the question was asked to find what was it? The largest integer less than or equal to d. So basically the floor of this is simply, of course, 66, and that's it. This is our answer. So 66 is the answer. Oh, I think it was below. Yep. Okay, very good. Let's move on. Now we have P is a convex polygon with 50 vertices, we have a set F of diagonals is said to be minimally friendly if any diagonal intersects at most one other diagonal in F at a point interior to P. So that means if we draw some diagonals, then we want to have this condition that each diagonal intersect at most one other diagonal. If we have something like this, then this is bad. We just want to have a single intersection, no more. And we need to maximize the number of elements in a minimally friendly set. Okay, that makes sense. So let's go and try to think about this. Let me add a page. Okay, so of course we were given 50 vertices polygon, and we need just to think about how many like how can we maximize the number of such diagonals so that we don't have any intersection. So now if you just like, of course we will not draw the complete one that they told us about, but let's draw something like this. And now of course you should try to play with this and try yourself to see what can you basically do in order to maximize the number of diagonals. So one of the choices, because we don't want to have many intersections, is to simply catch one point and try to draw all the diagonals from it, because now all of these are good. They don't have any intersection inside. So now we're safe. We don't have, the number of intersection is 0. So of course this one gave us, if we have n, then how many it gave us? It gave us simply n minus 3. So now we have n minus 3 till now. Can we do better? Because we still can do one intersection. So let's think about it. How can we do better? For example, if we catch this, then we cannot do something like this. We cannot join this nor that. So in fact, if you think about it, the only way, if we want to draw something from here, is to do this. If you do this, then you're good, because you just have a single intersection. But now if you catch this point here, then you cannot do anything actually, because if you going to here, then you already have 2 intersections, and you cannot do anything for this point. So if we use this point, but this point now is broken, so we need to move on here. So here what can we do? Again, you will easily see that the only thing you can do is this, and again this one is going to be broken. You cannot do it anymore. So now the only thing that you can do is do this thing here, and then actually now we cannot do anything. This one is broken. This one you cannot do anything to it. So of course right now this is not a proof for this is simply a kind of intuition. This is the best configuration we got. Actually the proof here is not easy, so you are expected in this the contest just to follow here your intuition. Like you need to try to do some figures, try some configurations, and see yourself which one is the best one. For example, you can try small n's and check that your configuration works. So here actually this configuration is the best, and we just are going to count how many diagonals that we got in order to find the answer. So far we have used 50 minus 3 to get just all of the diagonals from here, which is simply 47 so far. So we have 47. So now we're just going to count all of these. So how many of these do we have? If we think about it, okay, this one is deleted here. Basically here we're counting 1, and here we're counting 2, and then 3, and so on. So basically, how many vertices, like if we order them, this one, actually let's call it 1, this is 2, 3, 4, and so on. The last one is going to be 50. So we're going to see only the even ones. Each even one is going to have one diagonal coming from it, except the last one. The last 150 is not going to have anything. So that means it's just the number of even minus 1, which is 25, and 50 is not included, so it's 24. So it's 24. So if we add these together, we're going to get 71, which is indeed our answer. Again, as I told you, this is not a complete proof, but as I told you, here you're in this contest, you don't have time to work a complete proof. You need to follow your instinct here. Okay, let's move on. Question 19. Okay, Pn, they're defining it to be the product of the digits, and Sn is the sum of the digits. Okay, standard stuff. So we're going to have the following set: all the natural numbers such that Pn is non-zero. What does it mean, Pn is non-zero? That simply means that n itself does not have any digit 0, because if it has a digit 0, then Pn will be 0. Okay, so no 0 digits. And Pn is square free. Okay, this is nice information. If they told us Pn is square free, that means, for example, you cannot have 2 2's. If you have 2 2's, then this is bad. Same thing, you cannot have, for example, 2 and 6. This is bad. So now actually our choices are limited, because you can have 2, 3. For ones, you can have like as many ones as you want, so we don't have any condition on 1, but we have at most a 2, at most 3. 4 we cannot have even. 5 we can have. 6, if you have 6, then you cannot have 2 and 3. 7 is possible, a single 7. 8 is not possible. 9 is not possible. So these are our digits that we can use, and each one of them is at most 1. Okay, now what are they telling us? That Sn, the final condition is that Sn is a proper divisor of Pn. A proper divisor means it's not 1 and it's not the number itself. So find the maximum possible number of digits of the numbers in A. We need to maximize the number of digits. Yeah, so kind of find the the greatest number n that satisfy that. Okay, how exactly are we going to deal with this question? Yeah, as we said, we're just going to use these cases. So let's do that. So what are our cases? First of all, either we're going to have a 6, or just 2 and 3's. So let's say 6 in this case. So we can use 2, 3, 5, 7, and a bunch of 1's. Okay. And what they told us is we want Sn to be a proper divisor of Pn. And of course we want to maximize the number of digits, so we need to find the maximal n possible. So actually, if you think about it, we just want to have to add as many digits as possible. Right now the product here is at most 2 times 3 times 5 times 7, and like the sum is going to be 2 plus 3 plus 5 plus 7 plus the bunch of 1's. So if you actually want this to be maximal, the number of digits, then we should pick all of them for sure. Like we're going to pick all of these guys, and now we just need to find the sum, which is 5, 5, 10, 10 plus 7 is 17, 17 plus k1's. Divide this. In order to maximize the number of digits, then we need to pick the maximal k. So this thing is not going to be, of course, equal to this, but it can be equal, so that we have a proper divisor. We can just delete the 2. So if you just solve this, now this is the best k possible. Of course, we can just work this. So 21 times 5, 105 minus 17. So 100 minus 12, 90 minus 2. So it's simply 88. So if we pick 88 one, this is the best. And of course here, how many digits did we use? We used the 88 ones, and we used 4. So it's actually 92. Okay, so in this case, the best is 92. In the other case, if we have a 6, then we can only use, single 6. Actually, let's start in order. 5, 6, and 7. And a bunch of ones again. Or here, of course, also the same thing we can do. So now actually the sum is 5 plus 6 plus 7, which is simply equal to 18 plus k. It's going to divide the same thing actually, 5 times 6 times 7. So the best thing we can do, the exact same thing, 80 plus k. It's going to make it like this. So also 105, and we can think about it. The k is what exactly? Actually, here is the same thing, but k here is going to be 91. Oh wait, sorry, I messed up. It's not this, it's about this. So it's actually 87. Yeah, exactly, 87. So now we used 3 plus 87, that is 90. This is okay. This is best. This is actually, the previous case was better. So actually the answer is 92. Okay, very good. That was a very nice, lovely question. Let's move on. Okay, question 20. For any finite non-empty set X, okay, they're defining, max, the max function, okay, it makes sense, and the cardinality function. If n is the number of ordered pairs AB of finite non-empty sets, okay, we cannot have the phi here, of positive integers, such that we have two conditions. Max A times the cardinality of B is 12, and cardinality of A times max B is 11. Okay, this is actually interesting. For sure we're going to look at the second one, because 11 is prime. So we just have 11, 1, 1, 11. Okay, whatever, we need to find n actually, and then do some stuff about it to find, a 2-digit answer. But let's just count, n, the number of ordered pairs. Okay, for sure we're going, as we said, to catch the second equation, and to have two cases. Either the cardinality of A is 1 or 11, and we can play with the two cases. So let's do that, and by discussing, the two cases. Okay, let's do it here. So case 1. Case 1 was the cardinality, here actually, what was the equation? Yeah, cardinality of A. So case 1, cardinality of A is 11, and the max B is 1. This is actually, it's really simple. What does it mean the max B is 1? Remember, these are like positive integers, these sets. So if the max B is 1, then automatically the cardinality of B is 1, because it can have only 1 in it. So basically right now, let's keep that. We know that B is just the single number 1. But A, we know that the cardinality is 11. And now we can automatically know the max A from the first equation is 12. So now we know that max A is 12. So that means A is something like this. It's going to, to have bunch of numbers till A A10, then A11 is 12. So now we just need to count how many numbers here we can choose. Of course, we know that these guys can be just numbers from 1 to 11. So it's simply just the number here is 11, because in each time we just need to drop one number. For example, if we drop 11, then these numbers are from 1 to 10. If we drop 1, then these numbers are from 2 to 11, and so on. So actually in this case the answer is 11. Nice. The other case is the cardinality of A is 1, so A is just one element, and the max B is 11. So now A is just a single element, and the B we just think about its max. Now that means the second information tells us that the max A, which is just A, times the cardinality of B is 12. So now actually we have some cases, so let's do that. So now A is going to be one of these numbers. It's a divisor of 12, so it can be 1, it can be 2, it can be 3, it can be 4, it can be 6, it can be 12, and depending on each one of these cases we're going to have a cardinality. So of course we're going to to use that. Here we have 12, 6. I'm just actually going to flip this. 3, 2, 1. Okay, now let's think in each case. Remember that we know the max B is 11. So for the first case, if we know the max B is 11 and we have a cardinality of 12, this is a contradiction. We cannot have a max 11 and the cardinality of 12. At most, cardinality of 11 actually. So this case is refused. This case is refused here. Let's move on. For 2 and 6. Okay, right now, if A is 2, we don't have any condition, so let's just focus on B. So we know that the max B is 11. So now we just have remaining 5 elements. So we need to pick 5 elements out from the numbers from 1 to 10. This can be done, of course, by 10 chooses 5. So here actually is going to be 10 chooses 5. Next, now we'll be doing similar stuff. So here we're going to choose, okay, we drop 4, we drop 1, so it's 3. So now it's 10 chooses 3. And then of course 10 chooses 2, then 10 chooses 1, then 10 chooses 0. So this is actually the number of possibilities here. Of course now you can just calculate these guys here. So 10 chooses 5 is 252. 10 chooses 3 is, let me just check something, divided by 6. From here this is 4, this is 3. 3 times 4, 12. Okay, 120, yes. Okay, 120. 10 chooses 2 is 45. 10 chooses 1 is 10, and this one is 1. Okay, very nice. So let's add that. Yeah, 1 plus 5, 6. 6 and 2 is 8. Yeah, actually 428 here. So now of course we're just going to add the two cases. So 11 plus that. So the answer is going to be 439. 439. Okay, it was below. Yeah, 439. Yeah, we want to write this as 100 and A plus B. So this is 4 times 100 plus 39. So basically A is 4 and B is 39. So A plus B is just going to be 43. So the answer is simply 43. Okay, let's move on. Question 21. For some natural n, consider non-negative integer valued functions. Okay, on 1 to n, the domain is from 1 to n, satisfying f is basically f of I greater than or equal to f of j. That means f is non-decreasing. Okay, f is non-decreasing. And we have this weird condition, sigma I plus fi from 1 to n is 20, 23. We need to choose n so that the sigma of f is at the least. How many such functions exist? Okay, let's think about this question. Let me add more pages. Okay, let's work with the second condition. So they told us that the sigma of I plus fi from 1 to n. So this is basically the sigma of I plus the sigma of f of I, and we all know what's the sigma of I from 1 to n. It's, n plus 1 times n divided by 2. So basically, the sigma of f of I from 1 to n is equal to 2023 minus this. So in order to minimize this, they wanted us to minimize this. That means we need to maximize n. This is simply what they want. Okay, remember the function f they told us about is just a non-decreasing function. So okay, now we just need to find what's the maximal n, and what's the only condition. You can easily see that the only condition is that this thing is non-negative. You want this thing to be non-negative, so we just want to do something like this, and we need to figure out the value for n. So we can easily see that the best n here that works is n equals 63, and actually this thing is just going to be 7. So this is our best n, and now we need to find how many functions exist such that sigma f of I is equal to 7 from 1 to n. And now thinking about it, remembering f is non-decreasing, that means we just need here to create the function 1 2 till 63, and here's some numbers, like each one is going to be linked. The first few guys are all zeros, but here these guys, like the last ones, because it's the function is non-decreasing, are going to have some positive values, and we want their sum to be 7. So this is actually the number of partitions of 7. How do we count that? Well, easy. We just going to discuss all of them. So how many times can we write 7 as sum of positive stuff? So let's write all of them. 7, 7 is just one partition. 6 1 is 1. 5 2, 5 1 1, 4 3, 4 2 1, 4 1 1 1, 3 3 1, 3 2 2, 3 2 1 1, and 3 1 1 1 1, and 2 2 2 1, 2 2 1 1 1, and 2. How many ones do we need? Okay, that's it. And finally, if they're all ones. Okay, now let's count how many partitions do we have. So 1 plus 1, 2 3 4 3 2, and the number that means the answer is just, if we add these guys together, we're going to get 15. So the number of partitions is 15. So the answer is 15. For each partition, we can create one function easily. The first guys are zeros, and the last guys are the partition itself. Question 22. In an equilateral triangle, side length 6, we have pegs placed at the vertices and also evenly along each side at distance of 1 from 1 from each other. That makes sense. 4 distinct pegs are chosen from the 15 interior pegs, okay, on the sides. Each peg is joined to the respective opposite vertex by a line segment. Okay, that means we're going to choose 4 of them. Okay, we're going to draw these lines, and we want n denotes the number of ways we can choose so that the drawn line segments divide into 9 regions. We're going to have 9 regions. Okay, so this is actually something like this. If we draw equilateral triangle, side length 6, 1, 2, 3, 4, 5, and 6. So we just want, okay, let's actually do that for the others. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So what we'll be doing is we're going to pick 4 of these guys, these points, 4 of them, so that when we draw, like let's say we pick this, so we're going to draw this. Let's say we pick this, then we're going to draw this, and let's say we picked, for example, also this, and then we pick this. Then how many regions have we divided the triangle? 2 here. In this case, 1, 2, 3, 4, 5, 6, 7, 8. So here 8. So now actually they want us to divide it into 9 regions, and they want to count how many ways to do that. So let's think about this question. Remember, we need to choose 4. Of course, by PHP, by pigeonhole principle. Keep it in mind. Not the programming language, of course, PHP. So here we're going to have at least 2 on the same side. Let's assume it's this side. So at least 2, maybe like this and this, whatever. So let's do something like this. Doesn't really matter. Now, if we have the other one also here, another point on the same side, then as we said, of course, if we do this, we're not going to get 9, and if we do any one of these, we're not going to get 9. So no, this is bad. So that means we can just have 2 here. Now we're going to have somewhere else. So if we do have something like this, okay, now we have 6. But now if we do something like this, like 2 of them, then will we have what we want? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, so that's good. So that means if we just do something like this, 2 and 2, that will be good. But what if we do something like this? If we do something like this, let's count 1, 2, 3. Like this. Do this. 1, 2, 3. 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is bad. So does that mean that the only working solutions are 2 and 2 and 0 here? Actually, no, you need to think about this, because sometimes we might have some concurrent lines. If we have concurrent deviants, then this will actually mess up, because let's say this passed here. Now if you do the counting again, then 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is indeed a working one. So what does that mean? That means we're going to have 2 cases, either 2 by 2, and the other case is if we have 3 concurrent deviants and a single dude here. So we're going to just do that. So let's say the 2 cases. Case 1, the 2 and 2. So how many ways you can choose 2 and 2 here? So first of all, going to multiply by 3, to drop the sides that we're not going to discuss. And then here you have how many points remaining? 1, 2, 3, 4, 5. So 5 chooses 2, which is 10. 10 times 10. So in this case, we're going to have 300. Very good. In the other case, we're going to have concurrent deviants. How can we exactly have a concurrent sequence here? Well, of course, if you were talking about concurrent sequence, then you should think about Cephas theorem, right? So if we're going to have Cephas theorem, then we're going, to have, if we call, this over this times this over this times this over this is going to be equal to 1. Now, if you take the possibilities here, how can we make this 1? Because, like each ratio of these is going to be either 1 over 5 or, no, sorry, not 1 over 5. Yes, 1 over 5, correct, because the sum is 6. 1 over 5 or 2 over 4. 2 over 4 is just, 1 over 1 over 2, or 3 over 3, which is 1 over 1, or 2 to 1 and 5 to 1. So now if you take into consideration that these are the only ratios we can have, these are the only ratios, then that means, for example, if one of the ratios 1 over 5, then we must have another one that's 5 over 1, and that means the other one must be 1 over 1. So you see, we don't have done much possibilities. If you're going to pick either this, then this is going to be determined, and this as well. The same thing if you want to put 1 over 2, then you're going to have to choose this and this. Okay, very nice. But of course, we're going to have a possibility that all of them are 1, 1, 1. So if all of them are 1, 1, 1, then we just have a single possibility, which is 1. And if we're going to have, 1 over 5, then we're going to have 5 over 1 and 1 over 1. So how many ways to choose the 1 over 1? 3. And then the 1 over 5, it's simply 2. This one is now determined. Plus, if we're going to do the 1 over 2, then also 3 times 2. So, yeah, 6 plus 6 plus, okay, this is 13. So that simply means that here we have 13. So right now, if we add them up, 3, 1, 3, if we square, let me just double check that we did not miss something here. Here, this in case 1, 3 times 10 times 10. Yeah, the first case is as we said, if it's just simply 2 and 2, so you multiplied by 3 to choose, the bad side, and then 10 times 10, it's 5 chooses 2. Yeah, exactly. So no problem here. The other one is for, applied C. Okay, now I see what, like we did a mistake here, which is, okay, we counted these, but we did not count, the other, the fourth point. The fourth point actually can be anything. So in each one of these cases, we have a remaining point. So we have a total of 15 points. We choose 3. So now it's 12 points. So we can just actually need to multiply this by 12. Again, here we just were picking, the 3 points. We forgot the fourth point. So the fourth point can be anything. So it's actually 13 times 12. Okay, this thing is 44 plus 12. That is 5, 1. Okay, now if we add these guys, 6, 5, 4. So now if we add them, okay, what was the question? The question asked us to find the sum of squares, because the answer is a 2-digit number. So the sum of squares is 16 plus 25 plus 36. 2, 5, 7. Okay, 77. Okay, so that should be the answer. Okay, good. Let's move on. Question 23. Okay, we're going to have a coordinate plane. A lattice point is always, a point that has interior coordinates. They're giving us a point A at 1284, and find the number of right angle triangles ABC such that, okay, A we already have A, B and C we can play with them, they are lattice points, and they have a right angle at A, okay, nice, and the incenter is the origin. Oh, so they're giving us a condition over the incenter. Okay, let's think about this. We have space here. Okay, so let's draw the coordinates here. So point A is somewhere, let's say here. It was 12 and 84, and here is I, the incenter. Okay, and our triangle is something like this. And remember that I is the incenter. So, something like this. Of course, my drawing is very bad, but I is the... Okay, actually, if we want to make it better, if we just drop from I, the in radius, is this, and this, let's say something like this. If I extend these, yeah, something like this. Okay, let's think about it. B and C are lattice points, and I is the incenter. How can we translate, the idea that I is the incenter? First of all, you know that this is a square, and this is, R. But because we know what's this, we can, calculate it, because we can use this idea by Pythagoras. 12 square plus 84 square, we can take 12 as a common factor. Actually, it's going to be 12 times 1 plus 7 square, 50, so root 2, and 5 times that, so 60 root 2. So this is 60 root 2. This thing is 60 root 2. That means R itself is 60. Very nice. R itself is 60. So this is 60, 60, 60, 60, and so that means this thing is 60. Nice. The next thing we can see is that this line is determined already. It's not, a random line. The same thing is this line, because we know that if you just draw this, which is determined, now you just need to draw this to be 45 degrees. Same thing for this. So we can find the slope of this line is fixed, because the whole line is fixed. How do we find the slope of this line? We're just going to use this idea. You can use actually the idea of the tangent here. So if you have something like this is theta, and we draw 45, then this angle is theta plus 45. So the slope of this is, the tangent of this. The tangent of this is, going to, if we apply the tangent sum formula, this is just going to be equal to the sum of them, so the tangent of theta plus the tangent of 45, which is 1, over 1 minus their product, which is just tangent of theta. And what was the tangent of theta anyway? It's the slope of that. What is the slope? The slope is 7. So 8. So now it's minus 4 over 3. Okay, minus 4 over 3. So this is the slope. What's the slope of line AC? Easy. because these are perpendiculars, so that means you're just going to make 3 over 4. Okay, nice. So that means the slope of AB is negative 4 over 3. The slope of AC is just 3 over 4. Okay, if we have the slope, then we can find a relation between the coordinates of B. So that means that's y of B minus the y of A, which was this thing, over the x of B minus 12 is going to be equal to negative 4 over 3. Same thing for the other one, yc minus 12 is going to be equal to 3 over 4. Okay, now we can of course find the relation between xb and yb and xc and yc. Okay, so basically here we're going to get the relation between xb and yb, so that 300 is equal to 4yb minus 3xb. So actually from here, because xb and yb are integers, you can just put some conditions on them. So x, for example, is divisible by 4 for sure, so you can set xb to be for some number, let's call it k. So that so of course going to give you yb is going to be 75 plus 3k. Okay, same thing here. If we just set xc as it's going to also do the same thing here, 4 times, let's call it L, then yc is going to be 75 minus 3L, and now we just got the coordinates, and this condition is enough to tell us that B and C are both lattice points. Now we just need to handle the condition that this is 60, and in order to do this, how we're going to do it, we're just going to apply the distance formula. The distance formula, the point distance, if we have a point with coordinates xy, let's call them x0, y0, and we have a line with this equals 0, then the distance formula is simply you put an absolute value, you plug your point in the equation of the line plus c, and you divide this by root a square plus b square. So here we have the 2 points in terms of variables L and K. We can create the equation of the line, then we're going to plug the point 0, 0. So if you plug the point 0, 0 here, actually you're just going to have a single absolute value for c, and then the root of a square plus b square. So actually I'm really sorry, I'm not going to do this whole calculation for this question. It's really tiring, but this is the idea basically. As I told you, you have the 2 points, you can find A, B and C using L and K, and you can just apply this. This is equal to 60, and if you do that, you're going to get this. Okay, let me add space here. You're just going to get that L is just equal to 25 times K minus 13 over K minus 25. And now what we know from this is that this thing is an integer, L and K. So this thing is an integer, so K minus 25 divides this, but if you just use mod here, then K minus 25 must divide. K is, if you take mod this, the denominator, then K is 25, plug K 25 here. This is going to be 12. So K divide 12 times 25, which is 300. And any value for K that divides 300 will work. So that means, what are the divisors here? The number of divisors is 18, and that's it, we're done. So that means, no, it was below. The answer is just 18. This question, the only problem with it is the ugly relation that you're going to get, because when you want, you know, to find the A, B, and C we discussed, it's going to be a little tiring. It requires some calculations, but it's not that difficult. You can do it if you want. Next, question 24. We have a trapezium. Is a quadrilateral. Okay. Opposite sides are parallel. Okay, this is the definition of trapezium. Non-degenerate if it has positive area. Okay. Find the number of mutually non-congruent non-degenerate trapeziums. Okay, so they are distinct, and the four sides are in this set 5. The numbers from 5 to 10. Okay, let's think about it. Actually, let's say, you know, we're going to have these are the parallel stuff. So either we're going to have something like this, or we're going to have something like this. Of course, let me extend it more. Of course, these two guys are not parallel, so that it's a trapezium. Otherwise, it's going to be parallelogram. Okay, so you know we have these are the parallel sides, and we know, as we said, the four sides are in that set. So usually in these types of questions, the projections are very important idea. So if you hear, for example, drop, projection here, and a projection here. Let's call this one A, B. This is going to be A, this is C, and this is D. So right now, this thing plus this thing is going to be C minus A. This thing is equal to this, because this is a rectangle. So if you think about it, if you grab this triangle with this triangle, we're going to get this triangle. So that means this as C minus A, and B and D, these form a triangle, which is basically equivalent to the condition given. So that means that we just need to count how many possible triangles we can create, such that C minus A, B, and D, you know, they form a triangle, and A, B, C, D are in that set. In the other case, however, here we have A, and again this is C. So you can do actually the same thing. If we just project here and project here, you can do the same exact thing. You can, you know, grab this one here and put it here. This is going to be C minus A, this is going to be D, this is going to be B. So that just means that also we're going to have they form a triangle, C minus A, B and D. What does it mean they form a triangle? Right now, of course, our assumption is that C is greater than A, and let's assume that B is greater than D, so that we get distinct guys. Okay, right now we have these conditions, and we know that C minus A, B and D, they form a triangle. What does that exactly mean? Remember, if B is greater than D, so C minus A, this thing is between D plus B and D, B minus D. From here we get that A plus B is less than D plus C. This thing, you can think about it, it's actually a trash condition, because remember A and B and C are from 5 to 10. So this automatically holds, like, you know, here this thing, the smallest value, if you look at this actually always work. So you should just, you know, consider this and think about it. So now we just need to count how many A, B, C, D, such that C is greater than A, B greater than D, and as we know, they are distinct actually, and they are in the set from 5 to 10, such that A plus B is less than C plus D. Basically, you can just think about A and D or sorry, A and C, and you can figure out the other guys. Like you simply can do just discussion of cases, and that will be, you know, the idea of the condition. You can, for example, here pick A and B, and you can just see what is D and C. And actually, I will leave also these cases, like if you want to count these cases, to you. And I'm just going to say the total final answer is just going to be 31. But if you just list all the cases, and that will be it. Of course, I don't expect you to list all the cases, but what you should do is just fix two numbers, and count how many do we have remaining. It's really not that difficult. So just do the cases and make sure that your answer is 31. Okay, next. Find the least positive integer n such that there are at least 1000 unordered pairs of diagonals in a regular polygon with n vertices that intersect at a right angle in the interior of polygon. Okay, let's add the page here. This is an interesting question. As you can see, we're ignoring the details of the calculations, because otherwise the video is going to take too long. I tried to do the detailed calculations, and it was very long. So I'm just trying to leave the details for you to do, and I'm just going to say the idea of these questions. Anyway, this question now is really interesting, so let's think about it. So they're telling us simply that we'll be working with some like regular polygon with n vertices, and we want to have many like we want to have at least 1000 pairs of perpendicular diagonals. So we want to have diagonals that are perpendiculars like this. So the first idea is that we need to think, when exactly do we have perpendicular diagonals? So let's say we have in a regular polygon something like it's always going to have a circle, so we're going to have something like this, you know, whatever. And let's say that we know that these are 90 degrees. Can we get any condition on n? So if you think about it, right now we consumed 4 points, and furthermore we know that because this is 90, that this arc plus this arc, the measure is equal to this plus this. So that means if we here have, you know, A points, B points, C points, D points, then we know that actually A plus B is equal to C plus D. Again, you know, this is like really simple. As I told you, this plus this is equal to this plus this, the measure. And so, you know, the lengths of the arcs, you can think about it as that too. So you can easily see that the number of points here, A plus B, is equal to C plus D. So that means that the total number of points, which is n, is going to be equal to 4 plus A plus B plus C plus D, which is going to be 4 plus 2 times A plus B, which is even. So so we concluded that n must be even. So that means if we're going to have, you know, even just a single perpendicular diagonal, pair of perpendicular diagonals, then n must be even. Okay, that's very good. That means n is even. Next, now we need to see, can we find a formula to count how many pairs of perpendicular diagonals in an even, you know, 2n gone? So let's say we have 2n gone. How many pairs of perpendicular diagonals? We need to figure it out. Okay, how exactly are we going to think about this? So now if you just draw 2n gone and try to think about it, let's say something like this. and think about it. Let's sketch this, fix this one, this point, and if you draw this, then you already have a single diagonal. If you draw this, then you have two diagonals that you can choose, like to form a perpendicular here, one from here and the other from here. Okay, my diagram is not accurate. Oh, actually I think I messed up. It should be like this. Yep. So you get 2, and if you keep going, you know, you get more and more. So here you get 3, here again 2, and so on. So that means from a single point we're going to get something like this: 1 plus 2 plus 3 and so on. You can see when we have the same amount here and here, it's going to be n minus 1. Remember, here we're taking 2n1, so I immediately, you know, I'm not dealing with n, so 2n, so it's going to be n minus 1, and we're going to now we actually we will descend. So now n minus 2 and so on till we hit 1. So how do we calculate something like this? Okay, easy. Add n minus 1 again. So it's going to be 2 times the sum from 1 to n minus 1 and minus an n minus 1 that we already have. This thing is, you know, n minus 1 times n over 2. With the 2 it cancels, so this thing is n times n minus 1 minus n minus 1, which is just n minus 1 squared. Okay, nice. But now we just counted this. Now of course we have 2n points, so we need to multiply this by 2. 2n times n minus 1 squared. But now you need, of course, to think about if we need to divide by something, because now each diagonal we counted from here and here, so that means we need to divide by 2. But even this is not enough, because we're counting the pairs of diagonals, so that means we're counting this twice, once from here and once from there. So that means we need to divide it like this. So actually the answer is n over 2 times n minus 1 squared. Of course this is always even, this thing, because, you know, consecutive, so it works. So that means we just this is, you know, the number. We've proven, you know, this formula that the number of pairs of perpendicular diagonals is this, and now they told us it's at least this thing, so we need to find, you know, the smallest n, and n is clearly 14. So 14 works here. So remember, we're working with a 2n gon, so we need to multiply this by 2, so we get 28. So the answer is 28. I think we're working here or there. No, here. So it's 28. Okay, this was a nice combo question. Next question, 26. Okay, we're nearly done. In the land of binary, we have a unit currency is called bin, whatever. We have the denominations 1, 2, 2 square, and so on. Okay, because it's, you know, binary. The only condition here, the rule, is that we cannot in any transaction use more than 2 notes of one denomination. So we can only use at most 2 ones, 2 twos, 2 of the 2 squares. We cannot have 3 or 4. You can have 0, you can have 1, or you can have 2. Okay, and we need to find how many ways we can, you know, do 100. Okay, this is kind of a standard question. So how exactly can we do that? We need to find for 100. As we said, we can always use, it's the same kind of binary representation for a number, but in the binary we can only have ones and zeros. Here we can have twos as well. So this is, you know, the only change here. Okay, these types of questions usually can be solved using recursion. So let's think about it in a recursive way. And usually the recursion is going from n to 2n or 2n plus 1, something like that. So let's think about it. Right now, if we have an even n and we want to represent it something like this, 2n, as we said, sum of like powers like we want to write it in binary, but as we said, 2s are allowed. So if we think about the unit digits, the unit digit is what? The unit digit, it's either 0 or 2. It cannot be 1 because that means the number is odd. So it's either 0 or 1. So let's discuss the two cases. It's either 0 or it's 2. So in this case, this is 0. That means this here, this number represents the n actually. This number represents n. So this actually is an. An counts it. You know, I'm here just saying that an counts. Like a to n counts the number of ways to represent 2n, and an is to count like the counter for n. And if we have 2 here, then this number here is what? It's simply 2n. It's basically n minus 1 actually. Remember, you always need to divide by 2. So here we subtracted 2 and divided all of that by 2. So it's 2n minus 2 divided by 2, and that's just n minus 1. So it's a n minus 1. So that means we have the following relation, recursion. Okay, very nice. Now we need to build the same recursion for odd. For odd, it's even easier, because if we have for odd, then we already know that we can just have 1 here. If we have 1 here, then we have 2n. This is actually n. So that means we just have this case. So it's actually equal to an. So now we have these two recursions, and now our goal is to find 100. So let's do that. So 100 is even. We can divide it by 2. 50 plus 49. Nice. Now, of course, we're going to go descending, apply it again, apply the recursion again. 50, 25, 24, and 49. 2n plus 1, we can minus 1, 48, and divide by 2. So it's again 24. So it's actually 2 times that. Okay. 25. Now, A25, we can do the same, similar thing. Basically, we're just going to keep applying the similar technique until we get, you know, to smaller values that we already have the ability to find. So basically, right now we're going to apply the recursion again. For 25, we're going to get A12. Yes, A12. And this thing, A24, is A12 plus A. So actually, this is just going to be this. Okay, we're going to apply it again. You can easily see that it's actually just this. 3 A6 plus 5 A5. Apply it again. You're just going to get that 3 A3 plus 8 A2. Okay, finally, this thing is something we can calculate. So right now, if you just think about it, what are the first few numbers? So right now, n represents how many ways to represent a number n. So what is A1? How many ways can we represent 1 using that? Actually, you don't need that. Like, let's just count A2 and A3. How many ways can we represent 2? So A2, like, how many ways can we represent 2? Either, you know, just a single 2, or 1 and 1. Yeah, that's it. So it's just 2. And how many ways to represent A3? So 3, we can just 2 and 1. Yeah, that's 2 and 1. So it's just 1. So that means the answer is just 3 plus 8 times 2. And the answer is 19. Okay, nice. As you saw, this question is just a recursion, all about recursion. Okay, next, a quadruple of distinct integers is balanced if a plus c is equal to b plus d. We're going to take a set of any, you know, 4 numbers such that they're ordered, distinct, between 1 and 20, and the cardinality of s is 4411. Find the least number of balanced quadruples. Okay. So let's think about this question. So here, if you think about this question, we have something that's called balanced quadruple. But what we are going to do is we're going to pick some set S of let's call balanced sets bad, because we want to minimize. Actually, they're asking us find the least number of balanced, so we want to minimize it. So let's call them like bad. We have good and we have bad. So we're just going to pick a set of random, A, B, C, D between 1 and 20. So they are going to contain some good and some bad. We want to minimize the number of bad. We know that the number of goods plus the number of bad, it's equal to the total. How many ways to pick, 4 numbers from 1 to 20? It's just 20 chooses 4. So we know that in total. And if we can find what is the number of bad, that's the number of balanced, we can calculate that. Then of course we know the number of goods in total. So now if you pick a subset S, then of course the best way is to pick as many to pick all the goods, and if we need more, then we're going to pick some of the bads. So of course this will be our strategy. So if we can just figure out the number of bads, aka the number of balanced, then we'll be done. So how exactly can we think or can we figure out the number of balanced? Okay, so remember the balanced, the definition is we are going to have A plus C is equal to B plus D. So simply we can just go in ascending order. We discuss cases. So if A plus C, if both of them are equal to 5, how many do we have? Of course 1, because 1, 2, 3, 4. This is the only way. 1, 4, and 2, 3. So in this case we're going to have 1. If you look at this, equals 6, it's going to be we can just pair the numbers like 1, 5, and 2, 4. 3, 3 is always not allowed. So you will see that actually always the even and odd are going to have the same answer. So 1, 5, 2, 4. This is the only possibility. So it's also 1, also 1 in this case. If you move on, equals 7. Then now of course do the same thing. 1, 6, 2, 5, 3, 4. Now you can just think of it by picking 2 pairs. So it's 3 chooses 2 actually. Of course the even is going to have the same answer, so it's also 3 chooses 2. Then it's going to be 4 chooses 2 and 4 chooses 2, and so on. We'll keep doing that until we hit what number? Let's think about it. 20. If we do the similar idea, 1, 19. So we can do it for 20. 21. We can also do it 20. But if we move to 22, we're going to have trouble, because we cannot use something like this pair, because 21 is not allowed. Sorry. So that means if you think about it right now, it's going to be 2 times 2 chooses 2 plus 3 chooses 2, and so on, till what? 22 does not work, 21 works. But remember, we're always saying that odd, even. So odd, even, 20 will work. 20, of course, it will work for 20. So we're going to have something like this. And now here we don't have a 2. So let's figure out what are these. Of course, you can easily see that it's just going to be 9 chooses 2 here and 10 chooses 2 here. So now how will we continue from there? What about the 22 and these guys? So right now the only problem is this. We can just cross it out, and you will see actually that now we'll be going in descending order. So now the next one for 22, it's going to be 9 chooses 2. This will not work because, as we said, this is deleted. If it was the same, then it's going to have the same answer as 21, but it doesn't. So that means it's decreased by that much, so it's just 9 chooses 2. And then we're going to have the same thing again, so actually we just get this thing again times 2, so the answer is just this 4 and this. Of course you can calculate this easily. Here we can use the hockey stick identity again, so it's just going to be 10 chooses 3 times 4 plus 10 chooses 2. This is, by the way, the number of what? The number of balanced. The number of balanced. So if you can just calculate this, actually we're going to get 525. So that means the number of bad is 525. So what's the number? So okay, so we got that. So now, as we said, remember our cardinality of S, it was 4411. So what does that mean? That means that the total, which is 20 chooses 4, this one, what we're going to do is something like this. We're going, as we said, to pick all the goods, as much goods as possible, but then this will not be enough, so we're going to use some of these. So of course we're just going to do the remaining. So if you do the remaining, you will get like what you want, and you can easily do this. For example, you can figure out first of all how many goods here. This is the number of goods. So now once you calculate this, use all of these, then you're going to have a remaining. The remaining is the answer, basically is the answer. So that means the answer is just going to be this thing, subtract from it that, and the answer is going to be 91. So we're going to need to use, unfortunately, 91 of the bad or the balanced. Okay, that's it. Next, on each side of equilateral triangle, the side length n units, n is an integer, going to consider n minus 1 points. Okay, that seems similar to the previous question, which was 6 and 6. Okay, now we're going actually to draw a grid here. Yes, we're going to draw all, like going to have grid of congruent triangles. Okay, and then on each triangle we're going to have 3 coins. On each vertex we're going to have 1 coin. They're all up, they're all heads at first, and the possible move we can do is we're going to choose a single small triangle and flip the 3 coins on it, and our goal is to find all the values n from 1 to 100. It's possible to end up with all, like from the beginning we start with heads, all of them, then we're going to end up with tails. Okay, this is an interesting, very standard combo question. As we said, we're going to have something like this, and of course these as well. So we're just going to end up with a grid of these and these. Okay, anyway, how do we solve these types of questions? Very easy. We start with small cases. So for n equals 1, can we do it? Yes, we can. For n equals 2, can we do it? Let's see. Okay, like one very simple idea, you can play with it. If we actually pick all of them, this and this and this, if we apply the move each time, this is going to be flipped once, so that's good. Now it's tail. This is going to be flipped 3 times, so it's tail, and the same thing for the other. So yes, it works. Does it work for n equals 3? You know what, I can just extend this. Oh, come on. Okay, if I just extend that. Okay, so does it work for n equals 3? Well, if I apply the same strategy, this is going to become tail, good. This is going to become, okay, 1, 2, 3, 3 times, so it's also tail. What about this? 1, 2, 3, 4, 5, 6. Oh, 6, so it's still hit, so it fails. Of course, you can feel free to play with this, but you will always see that actually you cannot do it. So right now, actually, you know, one idea we can think of, exactly, this is not a proof written, so if you can use your intuition, is that simply when n is 1 and 2 mod 3 it works, 3 mod 3 doesn't work. And in fact, this will be the answer. Can we prove it? Well, yes, easily. We can do the same thing we did here. So if we have, you know, a triangle and divide it into triangles, then we can flip all of them. If we flip all of them, then you if you count for it, you will see that these vertices became tails, and each one of these, you know, it has three times, so it's also tails. So all of the points on the boundaries are now gone, and all the points inside, they're going to be, you know, 6, just like this point here. So they are going to be, let's say, one case. So we get actually kind of a smaller triangle by deleting all of these points on the boundaries. So now we started with n, we made it n minus 3. So you can use induction here. So anything that's 1 and 2 mod 3 will work. Our problem is to show that n equals n is 3 mod 3 or 0 mod 3 will never work. How do we show it? Usually the standard way is to find something that's invariant. How do we create invariants? If you have some experience, then these types of questions, you just can use coloring here. So here, of course, if we use 3 colors, here, if we color, you know, the points, for example, I'm just going to do the coloring for this case, and you can generalize yourself. Okay, so if I do 3 colors, 0, 1, 2, 0, 1, 2, 0, 0, 2, 0, 1. Of course, my goal is to try to make each triangle, each small triangle, have the 3 colors. So can I do that for multiples of 3? Let's see. 1, 2, 0. Yeah, we can. So now the idea is simple. Each time we're going to choose a triangle and flip it, the 3 are going to change their parity, the number of ones, 2 and 0. So when you started, actually the number of zeros is here 4, the number of ones is 3, the number of twos is also 3. So now if you think about it, we want each one of them to be flipped an even amount of times. An odd amount of times. Like each 0 is going to be flipped an odd amount of times so that it becomes tails. But the problem is that 0 and 1, the number of zeros and number of ones, they are different in mod 2. Like one of them is odd and one of them is even. But since each time we're going to do, you know, the same thing, so each time we're clicking on any triangle and flipping the coins there, the number of zeros and 1 and 2, you know, these originally were 4, 3, 3. Each time the number of zeros that were hits is going to change in mod 2. The parity will flip. So here 4, for example, is going to become 3, then it might become 2, then it might become 3, then it might become 2, then 1, for example, then 0. But each time, in each step, it's always going to flip. But because these guys are different, we can never, you know, reach the last case that they're both zeros. Because if they're both zeros, that means they have the same parity. So this will always be different in parity. So that means, you know, it will not work, and that means n equals 3 does not work. So n is n is 3, 0 mod 3 will not work. So n is 1 and 2 mod 3 work. So that means the answer is just all the numbers from 1 to 100 that are 1 and 2 mod 3. That means, you know, 100 minus the multiples of 3, which is simply, you know, the final answer is 67, and we're done with this. All right, finally we're going to have the last two questions. Okay, the last two questions here. Question 29. So they are calling a number n beautiful if n is written in one and only one way, as like if we have a sequence a1 to ak. N is a1 to ak, we add them and we multiply them, they are equal, and they are telling us that a1 till ak, you know, it's a non we're writing them in descending order basically. So for example, 6 is 3 times 2 times 1, which is 3 plus 2 plus 1. So we were able to represent it in this way. And this is unique. That means you cannot find other numbers. For example, you cannot say 6 is 6 times 1, which is equal to 6 plus 1 plus, you know, something. This like you cannot do it in more than one way. So it's unique. So that means it's beautiful. 6 is beautiful. But 8 is not beautiful, because this one you were able to present it this way and this way as well. So the uniqueness is lost. Okay, we want to find the largest beautiful number that's less than 100. So here basically the technique we'll be doing is we try to observe what numbers are beautiful. So if you try to think about it, because, you know, we have these types of stuff, we should think about divisibility and, you know, number theory question. So if we have a prime number, if we have a prime number p, is it beautiful? So you can see that for the sum here and the product, we can play with actually ones here, because here, you know, if we add ones here, it will not affect this. We might play with ones. So right now, originally, if we have p and p just alone, is not enough, because k is greater than 1. So what can we add? We can add ones. We can add ones here. But the problem is this thing is always going to be greater than this, so they can never be equal. So actually, for primes, it will never be correct. Okay, what about if we have a number that is p times q? P times q, we can say it, you know, if we just use the pq and ones, like this thing as one block, it will not work for the same reason. So we should probably do this. P times q and times ones, and this is equal to p plus q plus ones. So let's say we used k once, so that means this thing is plus k. Actually, if you look at the size here, for sure pq is always greater than p plus q. You know, for p and q, none of them is 1. So that means we can just always play with the k. Take a good k to, you know, as pq minus p minus q, it will work. So yes, we can do it. We can represent it. But is it unique? Of course it's unique, because it's the only possible way. Like we can pick p and q. So that means all numbers that are in the form p times q, and by the way, p and q can be equal, no problem. They're all beautiful. But let's say we have a number pqr. Then actually you can play the same game. Pq as one block times r, you know, times 1 times 1, k times, which is equal to pq plus r plus k. You can choose a k, and this will be, you know, correct. But you can also play is p times q times r times, you know, single ones, okay, which is equal to p plus q plus r plus also a suitable k. So no, it's not unique. Any number that has 3 primes, it's like not beautiful. So that means only beautiful numbers are the numbers of the shape pq, and you can try to find the largest number that's, you know, less than that, and the answer is going to be 95. 95 is the largest beautiful number. Okay, finally the last question. Let dm be the number of the divisors. Okay, positive divisors. They're telling us r is the number of integers less than 23, such that sigma di is odd from 1 to n. Okay, let's think about it. What does it mean? Sigma di is odd. Okay, we're going to discuss the parity of di. The parity of di. This is actually very standard and very famous thing. You know that if a number n, we're looking at the I of it, the n of it, the number of divisors. You know, like the number of divisors formula is just alpha 1 plus 1 times alpha 2 plus 1 and so on till alpha k plus 1. If the number is of this shape, p1 to the alpha 1, p2 to the alpha 2 till pk to the alpha k. So if all the, like if one of the alpha was odd, then this thing is even. But if all of them are even, then that means it's a perfect square, and this thing is odd. So that means d is odd, dn is odd, if n is a perfect square. Otherwise, dn is even. Otherwise. Now, thinking about this, we really find that this question is really easy, although it's, you know, the last question, because that means that this thing is always even, so it will not change the sigma di unless I is a perfect square. So whenever you have a perfect square, things are going to flip. So if you start with 1, you will see that 1, of course, d1 is 1. So we already have an odd. So that means from 1 to 3, this is good. But from 4 to 8, it's bad. It's even. From 9 to 15, it's good. So now, if you do, you know, this strategy, we're going to keep doing this until the end. The end was 2023. You will see that actually the last one is 43 squared to this. This is good. So that means we just need to count how many numbers do we have here. You know, how many numbers do you have from number a square to number a plus 1 square minus 1. It's simply just 2a plus 1. 2a plus 1. So now you can just do that here. Same technique here. If you just need to find, you know, sigma of 2i plus 1, where I, so here I was what? Here I was 1. Here I was 3. So where I is odd. Okay, simply you can, you know, brute force this as I, you can write it as 2i plus 1 itself, like 2j plus 1. So basically, actually, you know, this thing is just 4j plus 3, I think. Yeah, j from 0 till, okay, if we do it the opposite way, like minus 1, it's going to be better. You can start from 1, and here the last number basically is going to be what? Here, you know, 3, 7, 11. The last number is going to be 87. So what is, you know, the good j that's going to give us that? So for example, here it was 1, here it was 2, but you can simply calculate this. 87 is going to be 88 divided by 4, so 22. Yes, so to 22. Okay, now we can calculate this easily. 4 times 1 plus 22, 23, times 22 divided by, okay, so 11, minus 22. Yeah, so this is the answer. So now you can calculate that, and you'll see that the answer is just 990. The question was find the sum of digits, so it's basically 18. So that means the answer here is 18. And finally, we are done. Alright, so as a summary, we saw that in this paper, in this IOQM paper, it was first of all really lengthy, because we, like, each question, of course, like, you're not expected to solve all the questions inside the exam. In fact, what I saw through my quick search here is that students who got 10 points, 10 points, at least 10 points, they qualified to the next round, which is RMO. So basically, if you solve just 5 of these questions, then you should be safe. So even if you solve here 2 of the 5 mark question, then you should be safe. So that means, of course, in this particular paper, I'm not talking about IOQM in general, but in this particular paper, according to what I saw from the qualifications, so that means, okay, if you just solve 2 of the 5 mark questions, then that's enough. So this is not that difficult as we saw in this video. And one bad thing is that we have tons of calculations in most of the questions, which is really time consuming and really kind of difficult, because you don't want to miss the points. So you should always double check your calculations. And we saw that in many locations we were going to this to basically make calculation mistakes, or something like we forgot to divide something by 2, or some edits, so forgot to count some stuff. So this thing is really the most important thing. So in these types of tests, what you should do is that if you find a question that's very time consuming, then skip it, no problem. And you can always work for the 5 marks questions. This is also a good idea. But also what we saw is that they assume that you already know lots of stuff. So usually in regional math Olympiads, we don't discuss the in radius and basically x radius and these types of formulae. But here they assume that you already know all of these. So this is one thing you should keep in mind if you're preparing for IOQM. You should know all of these identities. You should be comfortable working with in combinatorics. You should be comfortable working with combinations. We saw that the hockey stick identity, for example, and these types of tricks on the combinations, you should be very comfortable with recursion also. In geometry, you should know also many stuff, like we saw that we needed to find the x radius, the formula for it. So you should also lots of identities regarding that. And the number theory, of course, the standard stuff, the mode, the divisibility, these are of course must for any regional math Olympiad test. You should always keep that in mind. Okay, my friends, so that was it for this paper. And let me know in the comments what other regional math Olympiads do you want me to discuss. And please don't forget to like, share and subscribe to my channel, and see you guys in the next video.